ADME WorkBench Video 2. Overview of ADME WorkBench capabilities. ADME WorkBench provides an array of predictive PK methods, which can be assembled and configured in a variety of ways, depending on the needs of a particular PK study. In this video, we'll look at these various techniques and discuss the types of problems to which they can be applied. Two general approaches for predicting in vivo pharmacokinetics are supported in ADME WorkBench: Allometry, based in the Wajima method, and physiologically based pharmacokinetics. Each of these methods in turn uses a variety of sub-methods to compute necessary PK quantities based on the available inputs. In general, selection of a predictive method is determined by the nature of the data available for input. Allometry requires in vivo blood or plasma time course data for one or more preclinical species. PBPK models can utilize a wide variety of data, but are most useful when only in vitro and physicochemical data are available for prediction. A brief summary of the two general methods is presented here. A more detailed description of these methods and supporting sub-methods is presented in the PK prediction methods section in the ADME WorkBench documentation. When in vivo preclinical data is available, ADME WorkBench can use allometric techniques for predicting human PK. The allometric scaling techniques used in ADME WorkBench, named the Wajima method, is based on the observation that blood plasma concentration curves versus time are similar in shape across different species. Moreover, if these curves are properly normalized, meaning time and concentration axes properly scaled, the curves can be superimposed. In this case, the time axis is normalized by dividing the time coordinate by the mean residence time, or MRT, and the concentration axis by the steady-state concentration, or CSS. Thus, to predict IV kinetic in humans, for example, the concentration curves for preclinical species may be normalized by using the measured mean residence time and steady-state concentration, and then scaled to predict human PK by multiplying the time and concentration coordinates by the predicted human MRT and CSS. Human MRT and CSS are computed using the relations MRT equals VSS over CL and CSS equals dose divided by VSS, meaning a prediction of human volume of steady-state distribution and clearance are required. ADME WorkBench provides a number of methods for predicting human VSS and CL from preclinical in vivo data. These methods are described in the documentation in the clearance prediction and steady-state volume of distribution sections. To determine PK for orally delivered compounds, values for Ka, the first-order absorption constant, and F-abs, the fraction oral dose absorbed, are estimated from preclinical species data. These values are then averaged to estimate human Ka and F-abs. This method is described in further detail in the first-order uptake rate and fraction absorbed section in the ADME WorkBench documentation. The PBPK method utilizes a generic whole-body PBPK model to predict tissue and subtissue level concentrations in a variety of tissues. The PBPK model used in ADME WorkBench is highly configurable. The submodels used to predict absorption, distribution, and metabolism and elimination can individually use a variety of techniques depending on the particular input data available. Since the PBPK model includes representations for individual tissues, predictions can be made of concentration profiles at the tissue level. By changing the appropriate physiological parameters, the model can be reparameterized to predict kinetics for non-human species. Use of the PBPK model also allows the effect of phenomena such as gut metabolism and active influx efflux transporters to be explicitly included in the model. The absorption model of ADME WorkBench can use either a first-order absorption formula, where the rate and fraction absorbed are estimated from preclinical in vivo data, or it can use a multi-compartment GI system model, sometimes called ACAT, which predicts absorption by modeling the dissolution and permeation of a compound across the intestinal tissue based on the physicochemical properties of the compound and Keiko-2 permeability information. The ADME WorkBench PBPK model predicts distribution of compounds using partition coefficients, which can be calculated in a number of ways. In cases where preclinical in vivo data is available, partition coefficient values can be determined by scaling techniques based on observed volume of steady-state distribution values in certain preclinical species for both lumped and whole-body PBPK models. Alternatively, partition coefficient values can be computed based on compound physicochemistry and tabulated tissue composition data. These techniques additionally allow prediction of concentration at the tissue cell and interstitial fluid level. ADME WorkBench provides a variety of metabolism models for use in PBPK. At the highest level, metabolism may either be scaled from in vivo clearance values observed in preclinical species, or it may be computed using in vitro in vivo extrapolation techniques. Both linear and saturable metabolism are supported in both methods. For IV-IVE, clearance may be predicted based on hepatocyte or microsomal in vitro studies, with optional corrections for protein binding. Metabolism in both liver and gut tissue is supported. ADME WorkBench includes two methods for modeling renal excretion. One method uses a measured or estimated total renal clearance, which can be either linear or saturable. And the second method predicts renal clearance by accounting for glomerular or filtration rate, active tubular secretion, and reabsorption separately. Active secretion can in turn be based on total secretion value or an unbound intrinsic value. Analyses in ADME WorkBench may be conducted in either batch or interactive mode. In batch mode, the analysis for each compound is a list, and a list is executed sequentially, and all results are presented at the end of a run, allowing PK profiles and results to be compared between compounds in the list. In interactive mode, a single compound is analyzed interactively, allowing you to manually adjust parameters and see the concentration profiles updated in real time. The PK and PBPK models used by ADME WorkBench are specified in the form of CSL language source code files. CSL is a programming language created specifically for encoding continuous time models consisting of systems of ordinary differential equations. CSL is both a text-based and equation-based language, meaning the equations which comprise the PK or PBPK models are specified in human-readable form. Source code for the models used in ADME WorkBench is contained in the Models folder under the ADME WorkBench installation directory. One subfolder named PK under this directory contains the CSL source code for the compartmental PK model used to estimate PK parameters from in vivo data. The other folder, named PBPK, contains a set of CSL files which implement the whole-body generic PBPK model used in ADME WorkBench. The various CSL files in the folder implement specific submodels used by the main PBPK model. The ADME WorkBench PBPK model and the individual absorption, distribution, and metabolism submodels are discussed in further detail in the physiologically based pharmacokinetic models section of the ADME WorkBench documentation. This concludes the ADME WorkBench capabilities overview. In the next video, we'll look at the ADME WorkBench user interface in more detail.